Alright, this video is part 4 of a lesson covering quadratics. So far we've done a lot of factoring and solving by factoring and completing the square. We're going to throw a few curveballs now, and starting with graphing quadratic inequalities. Greater than, less than. And a couple of error analysis problems, and then some review problems. Rate of change, dealing with fractional exponents, some review stuff, and finishing up with intervals of increasing and decreasing. Really not so much about the quadratics as a general function analysis. Okay, no matter which way you do it, the first thing you have to do is factor this so you can find the x-intercepts of this parabola. So factoring this is going to look like this. Alright, x squared, that's x times x, right? 5 can only be factored as 5 and 1. Now, inner plus outer has to equal the middle, so we're shooting for a middle of negative 4x. Inner, I have 5x. Outer, I have 1x. If I want a negative 4x, I need a negative 5 and a positive 1. So there's my negative 5 and there's my positive 1. Luckily, a negative 5 times a positive 1 does make a negative 5, so this is working out great. Okay, now I need to set these factors equal to 0. So I'm going to do something like this. X minus 5 equals 0, and x plus 1 equals 0. Why am I doing equal and not greater than? Because I'm looking for the x-intercepts. I want to know where the parabola touches the x-axis. I want to know where it equals 0, because that's where it's going to change from greater than to less than. This will be the border between greater and less. Okay, anyway, enough speeches. I'm going to add 5 on both sides here. I'm going to subtract 1 on both sides there. And that's going to give me x equals 5 as one of my x-intercepts, and x equals negative 1 as my other. Okay, so negative 1 and 5. So as we record that on our number line, let's put 0 on here, of course, and I already forgot. Negative 1 and 5. So negative 1 is going to be like over here somewhere. Alright, brilliant. And 5 is going to be like here. Will I graph these as open circles or closed circles? Well, because this is greater than, not greater than or equal to, I'm going to leave these as open circles, alright, to show that the border points here, the endpoints, will not be included in the set. We want to know where the function is greater than 0. These points are equal to 0, so they are not to be included. So, shall we do this the easy way or the hard way? I'll do it the easy way first and then the hard way. The easy way is graphically. Alright, if you are at all a graphical thinker, if you're a visual thinker, then the following will be easiest for you. When you look at this, and you know it is a parabola because it is quadratic. You know it's an upward facing parabola because the leading coefficient is positive. So what you should do is picture this upward facing parabola, and you can go ahead and draw it. Okay, you got this parabola like this, and it has these x-intercepts as discussed. Okay, now you look at the inequality here. And this is saying where is the parabola greater than 0? Okay, when you see greater than, you should be thinking above. Okay, so where's the function greater than 0? Well, graphically, that's where the function is above 0, meaning above the x-axis. So these are the zones where the parabola is above the x-axis, thus greater than 0. So if you understand that when we solve these problems, 19 times out of 20, we're either going to get an inside graph like this, or we're going to get an outside graph like this. Okay? Given these choices, it's pretty obvious that this is the outside graph. Okay? Because we have a branch going to the left and a branch going to the right. Okay? So that is what we were dealing with. So we've got, alright, so these will be the x values that give us the parabola greater than 0 here on the left, and these will be the x values that correspond to the parabola being greater than 0 on the right. And so that's the graph, and we also need the solution set, interval notation and whatnot. So using interval notation, I could write this as the left branch. How far left does it go? That's a good question. It goes to negative infinity. How far to the right does it go? Well, it stops here at -1. Will I put a square bracket on there? No. For the same reason I put an open circle, we're not including this, so we can show that with a round parenthesis. And then we'll put a union symbol and join it together with the right branch interval. So how far left does it go? Well, it starts here at 5. Okay, how far right does it go? Infinity. Okay, so this would be the interval notation of the solution. Okay, so we've got the solution, we've got the graph. Now, if I wanted to, I could have given you an inequality instead of interval notation. So I want you to know how to do that. So this branch here on the left, these values are less than -1. You see the arrow going to the left of -1. So I could have, instead of writing this, I could have said x values less than -1. Similarly, this arrow over here to the right of 5, these values are x values that are greater than 5. Okay, instead of the union symbol, I just used the word or. So this purple is another way you could have done it instead of interval notation. Okay, that's for my graphical thinkers. And that's the way I think of it. If you're not comfortable, if you didn't understand the parabola thing and why it turned into this, then instead you can think of it this way. You can think of it as we have divided the number line into 3 zones. And you can use test values to see where the solutions are. So you could have done it this way. The 3 zones are, we have one zone here on the left, we have another zone here in the middle, okay, and we have another zone here on the right. Alright, 3 zones. So you can just pick a value from each zone to test out. So from the yellow zone, I would use, for example, x equals -2, just anything over in the yellow zone. In the middle zone, the blue zone, I would use x equals 0. I always use 0 when I can. In the pink or red zone, I would use, for example, x equals 6. Now the idea is to substitute those values back into the original equation. But instead of using the original equation, I would use the factored form. Alright, x minus 5 times x plus 1. Okay, so here I go. X minus 5 times x plus 1, and we want it greater than 0. Okay, x minus 5 times x plus 1 greater than 0. Alright, x minus 5 times x plus 1 greater than 0. Okay, and we'll just plug in these test values. So if I put in -2 for these x's, this becomes -2 minus 5, -2 plus 1. Alright, so this becomes -7 times -1. Okay, and negative times negative is a positive, so this becomes 7 is greater than 0. Is 7 greater than 0? Why, yes it is. Alright, that means x equals 2, negative 2 is a solution to the inequality, which means all of these yellow values are solutions. So I will show that these yellow values are solutions by drawing in an arrow. Okay, which is just what we had by the other method. Now, looking at the middle area, the middle zone, if I let x equal 0, then I've got, oh, I meant to do gray. Okay, then I've got 0 minus 5 and 0 plus 1, but that's just negative 5 and 1. So that's just negative 5. Now, is negative 5 greater than 0? No, negative numbers aren't greater than 0, they're less than 0. No. That means 0 is not a solution. That means none of these blue values are solutions. And we will represent that by leaving this area blank. Alright, let me get rid of this as well. Okay, so we've done this. We'll leave this empty because these are not solutions. And now we just need to check the red zone. Okay, in the red zone here, we have, if we let x equal 6, then we've got 6 minus 5, 6 plus 1. So that's 1 and 7. So that's 7. Is 7 greater than 0? Why, yes it is. Okay, so that means 6 is a solution, which means all of these red values are solutions. And we will show that by drawing an arrow representing all of these solutions. Okay, and that gives us the same picture that we had last time, which of course will give us the same solution set that we got last time as well. Alright, so that's 2 ways to do it. Alright, choose wisely. Now let's glance at number 22, see if I can squeeze this into the same video. The following problem contains one error that has caused the final answer to be incorrect. Identify the mistake in the work by circling the error. Be precise. Then factor the problem correctly. Okay, so let's find the error. Okay, for me it helps to sort of do the problem myself, side by side. So, fine, they have 2x squared minus 18, right? What's the first step of factoring? GCF. So, the next thing I would do is I'd pull out the 2, and that would leave behind x squared minus 9. Okay, they have that. What would I do next? I would look at the x squared minus 9, and I'd think to myself, hey, that's the difference of 2 squares. I'm going to factor that down. How does x squared minus 9 factor down? Well, that factors as x plus 3 times x minus 3. Okay, which makes sense because positive 3 times negative 3 would make negative 9. Oh, look, I see what they did wrong. I'm going to be real precise. Here's the problem right here. Okay, this should have been positive. Alright, it should have been x plus 3 times x minus 3. Negative 3 times negative 3 would make positive 9. Alright, so you know that's got to be wrong. So, in fact, and here's the correct answer right there. Explanation of mistake. One of the x minus 3's factors. Whoops, what am I writing? School should have been x plus 3. Okay, so the correct answer, like we said, was 2 times x plus 3 x minus 3. Alright, that brings us up close to the 15-minute mark, so I'm going to go ahead and pause there, and I guess we'll have a 5th video. That's a lot of videos, so we'll have a 5th video to finish up this lesson. I'll see you on the next video, people.